Okay, so like in the last lecture, we have discussed O of n time complexity would require if we uh, use a matrix, right, to get this solution. So here the hint is given how actually we can find out. First of all, the square root the number, then square the number again. So this is the hint for this problem solution. Square root the number and square the number again. If the result is equal to the number, then the last light condition is turned on, otherwise off. And the same thing you have seen in the practical. But how actually? So we can discuss this thing. So the nth light bulb is toggle once for every factor of n. Okay. So nth bulb is toggle once for every factor of n. So squares are the only numbers with an odd number of factors, which can be seen because every factor j of a number has a cofactor k for which jk is equal to n. This pairs up all the factors of n unless j is equal to k, which only occurs when n is a square. Difficult to understand, right? But we can you can easily understand by considering one problem. Okay, so example is like 25. Okay, so 25. So if you as if you are taking a square, like 5 square is a 25, right? 5 square is 25. So here if it is here if it is like if you are taking a square and if you are getting a number, for this kind of number always you will find there is an odd number of factors. You will find odd number of factors like 1, 5 and 25. So how many factors are there? 3 factors are there. So 3 factors are odd factors if the square is possible, right? To take another example like 9. So 3 square. 3 square is what? 3 square is 9. So if yes, if the square the numbers is possible, then you will get odd number of factors like 1, 3 and 9. Like 4 square, that is 16. So the factors are 1, 2, 4, 8, 16. So again 1, 2, 3, 4, 5. Odd number of factors are there. And if any number which is not directly a square, like 5 is not the square of any number, so here you will find the factors are even factors like 1 and 5. Only 2 factors are there, and again it is even factors. Again if it is 6, and 6 is again not a square number of any number, so here you will find even number of factors like 1, 2, 3, 6. Okay, so I hope you understood up to this point the logic here. If it is a square number, then you will get odd number of factors, and if it is a non-square number, here you will get even number of factors. Now you can read again. So the light n bulb toggle once for every factor of n. Squares are the only numbers with the odd number of factors. So squares are the only numbers which get odd number of factors like 3, 3, 5. So odd number of factors. So which can be seen because every factor j of a number has a cofactor k for which jk is equal to n. These pairs of all the factor of n unless j is equal to k, which only occurs when n is a square. Now we'll see this term explanation further here in this program. Now how actually you will find out, like suppose if you are taking any number which is the square is possible like 25. So 25, if you will find out the square root of 25, that is 5, right? That is a 5. And again, if you will take the square of this 5, you will get the same number, that is a 25, correct? But if you are taking a value of 5, so square root of 5, you will get a number which is not exactly the one number, you will get the answer in a something in a point, right? What will be the under root of 5? Which value you will get for under root of 5? Square root of 5? 5? Square root of 5, not 25. For 25, it is right. Neeraj said 2.23, right? It is 2.23. 2.23. Okay, so 5 square is what? 25. But if you are taking 2.23 square, you will not get 5, right? You will not get 5. You will get something different number, which is not exactly 5, right? If you will take 2.23 square, which is not exactly 5, that the number would be something different. So whatever input you are giving, if that input is satisfy this condition, accordingly you can identify the condition is false or true. It will inform you the last bulb position, either it is off or on, but it is based on ith term, at which turn he is going. For example, it is he is going at 25th turn, or he is going for the 5th turn. Based on that, the last bulb position will be decided. So here you have implemented this program in the practical. Now you can understand this program very easily. You are taking one number here. For example, you have taken 25, right? So we are putting this 25 in a loop, and we'll check it. If the number is 0, if it is 0, here it will break, because 0th turn, so obviously it will break. If it is, then what we are doing here, we are taking a square root of that number, and we are putting that value here in a temp. Okay, so 25, the square root of 25, that is a 5. Okay, and temp into is equal to temp. What it means? Temp is equal to temp into temp, right? Temp into temp. So in temp, what we are doing, 5 into 5, that is 25. So in temp also 25, right? And in a number here we have given, that is a 25. So 25 is equals to 25, yes. So that time it will print yes, it means the bulb is on. Otherwise, the bulb is off. So when it will happen that, like, if it is the complete square number, only that time you will get this condition, only that time only this condition will satisfy. Otherwise it will not satisfy for this number, which is not a complete square, right? So this is the logic for this problem, which is very simple, and you can easily implement this program into your practical. Okay, so mainly this thing that you have to understand, and by this way actually we can solve the problem. So we'll see the second problem, that is Carmichael numbers, right? Again, so first we'll discuss theory part. Like, certain cryptographic algorithms make use of big prime numbers. However, checking whether a big number is a prime is not so easy. So we have seen in application the cryptography uses prime number for the cryptographic algorithm. But again, it is very difficult to identify a big number is a prime number or not. So randomized primality tests exist that offer a high degree of confidence of accurate determination. So actually, to determine a big number is a prime or not, one randomized primality test is available. By the confidence, you can accurately predict the number is prime number or not. And we can determine that number in a low cost by using a Fermat test. So by using this Fermat test, we can, in less time, in less calculation, we can predict a big number is a prime or not. Let A be a random number between 2 and n minus 1. So 2 and n minus 1, any number where n is the number whose primality we are testing. We are testing any number is prime or not. Then n is a probably prime if the following equation hold. So that time n would be, you can say, is a prime number if and only if it hold this equation a raised to n mod of n is equal to a. Okay, so if any number is there in between 2 to n minus 1, 2 to up to the n minus 1, and if you are putting that equation value into this equation a raised to n mod of n is equal to a, then we can say it is a prime number. But what is a Carmichael number? So if a number passes the Fermat test several times, then it is a prime with a high probability. So what we can do, we can continuously check that number for the prime number. Okay. And if he passes multiple tests, then we can confidently say, right, okay, this is a prime number. With high probability, we can say this number is a prime number. So unfortunately, there's bad news. Like certain composite numbers, which are non-primes, still passes this Fermat test. But there are some numbers which passes this Fermat test. One example is like 561 is passes this test. So certain composite number non-prime still pass the Fermat test with every number smaller than themselves. So these numbers are called Carmichael numbers. Okay. So by this method, by the Fermat test, you can find out any number is a prime number or not. But unfortunately, there are some certain composite number that you can recognize like it is a prime number, but actually it is not a prime number. So that time you can say it is a pseudo prime number, which looks like a prime number, but actually they are not a prime number. Hmm? So in that case, we can say that numbers are called Carmichael numbers. So what you have to do, you have to write a program for the Carmichael numbers, and that you have done in your practical. Hmm? So pseudo prime. So there is an equation actually to calculate it. So there are number of steps are there, like 561 you have to identify it is a prime or not. So we have to identify their factors, right? So the factors are like, for example, the factors are 3 into 11 into 17, right? 3 into 11 into 17, that is 561. Okay. So we can identify these factors by simply like 561 and then 3. So when you will divide by 3, you will get 187, and then the 11, then you can divide by 187. So here you will get the 17. Okay, and then here we use a 17 and 1. This way 3 is a 170. These are the factors. Then you can put this value into the Fermat theorem. In Fermat theorem, like a and a comma 3 is equal to 1, a comma 3 is equal to 1, and like a power of a raised to 2, a power of a square congruent of 1 mod of 3. So this is a format theorem for 3. So and so forth, we have to check for the 11 and 17. So for the 11, like a comma 17 is equal to 1, like a raised to 16 congruent of 1 mod of 17, right? And then we have to use, now we'll check for 561. So 561, that is 560 is equal to uh, a square the whole bracket 280. So 280 into 2, that is 560. In this way we can bifurcate these values, and finally we can write like a raised to 560 congruent of 1 mod of 561. So here actually it is a pseudo prime numbers, which is not actually prime number, but it looks like it is passes the Fermat test. So that time we can say it is a Carmichael numbers. Okay, so there is an equation for this to find out the Carmichael equation, like power of b raised to n minus 1, b raised to n minus 1 mod of n is equal to 1. Okay, so this equation is there to find out the Carmichael numbers for all b is ranging from 1 to n. So to find out the absolute pseudo prime number, or we can say the Carmichael number, the equation is this, uh, b raised to n minus 1 mod of n equal to 1, right? Or you can say b raised to n minus 1 congruent of 1 mod of n, right? Anything you can use the equation for this. Now, what is the value of b? B is ranging from 1 to n. This b is ranging from 1 to n, such that b and n are relatively prime. So any number, but the condition must be satisfied that b and n are relatively prime. Relatively prime already we have seen in theory part, like how we can find out by the GCD b comma n is equal to 1. If it satisfies the condition, then we can choose for, we consider it for relatively prime. So we can say n is pseudo prime if and only if n is a composite number, and the second condition b raised to n minus 1 congruent of 1 mod of n for all integer of a with a comma b comma n is equals to 1. If it will satisfy, then only we can say it is a pseudo prime number. Okay, so uh, so this equation and this condition we have to use. This condition we have this condition we have to use to identify the number is Carmichael numbers or not. I hope you could understand what is a Carmichael number. Carmichael number means a pseudo prime number. Pseudo prime numbers means we satisfy the Fermat test, but actually the number is not a prime number. So that number belongs into the Carmichael numbers. So this is the equation that we have to implement our program to which satisfy this equation. Power of b raised to n minus 1 mod of n is equal to 1. So if you are giving a n value 8, so 8, so by using a Fermat test, it will set this is a prime number or not, so false. So 8 is not a Carmichael number because 3 is relatively prime to 8. Okay, so in this way actually we can find out the Carmichael numbers. Okay, so now the program is very simple. Now here we have to use a number which is in between 1 to n such that b are relatively prime. So 1 is not a prime, so that's why we have started from 2. So b is a relatively prime to n. So obviously we have to start from 2 because relatively prime. 1 is not relatively prime. So 2 to n. Okay. So for loop we have used, and there's a two condition that we have discussed. The one is GCD b comma n is equal to 1, right? So this is a 1 condition. So we are checking for this condition if GCD b comma n is equals to 1. So what we are doing, we are using a for loop. So one by one, we will consider a value from here, and it will, in here we have up to the n, the for loop will rotate, right? And we check it is a Carmichael number or not. So up to that point, which is obviously less than of the n, right? Less than of n. In theory part already we have discussed this thing. So if GCD b comma n is equals to 1, the first condition, and second is what? The b raised to n minus 1 mod of n is equal to 1. Okay. So if power of b raised to n minus 1 mod of n is not equal to 1, if these two conditions are there, and that time it will return a false. Otherwise, it will return a true. So it will return a true for the Carmichael numbers. So according to the Carmichael numbers, if both the conditions are satisfied, then it is a Carmichael numbers. If it is false, that time it is not a Carmichael numbers. So again, this program is very simple that you have implemented in your practical to identify the number is a Carmichael numbers or not. Okay. So you have to practically implement all these programs and check on your computer so that you can easily understand. The next problem is based on Euclidean algorithm. So already we have discussed Euclidean algorithm in previously, but briefly I will take a recap of Euclidean algorithm. Mainly we use this Euclidean algorithm to find out the GCD. Okay, so simple way to find a GCD is to factorize both. How actually we can find out the GCD like 36 and 60 number? So we will factorize it 2 into 2 into 3 into 3. This is a 36. Similarly for the 60. So which are the common factor here now? 2, 2, 3, 2, 2, 3. So simply we will multiply it and we will get the GCD, that is a 12. So 12 is the GCD for 36 and 60. But how we can calculate by using Euclidean algorithm? So I hope in the last lecture we have seen the Euclidean algorithm to calculate the GCD. Right? This algorithm we have discussed in the last lecture. I hope you could remember. Like GCD AB. So formula is what? GCD B comma A mod of B. So simply we are shuffling here B comma A mod of B. And then GCD A0 is equal to A. So finally we will get the A. So this example here we have considered GCD 1025 comma 35. So according to this formula, B came to at this point and then A mod of B. So 35 is here and 1025 35 mod of 1025, you will get the GCD A mod of B, you will get the 10. So 35 and the 10. So again 35, 10. So what we will do, 10 come to at the first side as per the formula, B is here, and 35 mod of 10, you will get the 5. So 10 and 5, again this 5, B come at this side, so 5 is here, and then again 10 mod of 5, so smaller number. So 10 mod of 5, 0. And now here the 0 term got A comma 0 is equal to A. A is what? A is 5. So 5 is nothing but the GCD. So in this way, the Euclidean algorithm works by which we can find out GCD in less cost. Okay. So about the extended Euclidean algorithm. So in extended Euclidean algorithm, we have discussed uh, this similar type of equation already in theory part, but it is an extension of Euclidean algorithm to find out the coefficient of x and y. So in here we have to calculate the value of x and y in Euclidean equation, right? Ax plus by GCD of a comma b. So similarly here you could see ax plus by GCD a comma b. So this extended Euclidean algorithm is nothing but the Diophantine equation, right? So by using this Diophantine equation, we can find out the value of x and y. Already we have seen how to calculate the value of x and y by using Diophantine equation. So input is given, like a and b value is given. We have to identify the value of x and value of y. So here in the output, so this is the problem, and you have to find out the solution. For you, how you will get the solution? You have to find out the value of x and value of y. So in the output, you will get the value of x, that is 1, and y is -1. Simply you will put this value 30 into 1 plus 20 into -1. You will get the answer, that is 10. Okay, this 10, you got uh, the solution. Okay, so this is the problem statement in which you are giving the value of a and value of b, 35 and 15, and you will get the solution of by calculating a value of x and value of y. So here x is 1 and y is -2. You are getting the answer 5. Okay, so this is the input and this is the in output. You are getting like this. 5 is the output and x value is 1 and y value is -2. So you have to implement a program for extended Euclidean algorithm. So extended Euclidean algorithm name is the Diophantine equation. So we have seen the Diophantine equation, how actually we have repeatedly calculate uh, how we have calculated the remainders and how we have put it the values and calculated this. So the extended Euclidean algorithm or Diophantine equation updates the result of GCD A B using the results calculated by recursive call GCD B mod of A comma A. So how GCD A comma B, like Euclidean algorithm, what we are doing in Euclidean algorithm, we are calculating B comma A mod of B. So here we are simply the same way, we are calculating B mod of A comma A. So let value of x and y calculated by the recursive call be x1 and y1 into x and y are updated using below expression. So this recursively we have to use this equation to calculate the value of x and y, and here the x1 and y1 values are recursively called and it is replaced, updated, right, until and unless we will get the value of x and y. Now for the x the value is like y1 minus b divided by a into x1. Like here, ax plus by is GCD A comma b. So here, suppose if you want to find out x, so what we have to do, b divided y1 minus b divided by a into x1, and y is calculated y how by the y is nothing but your x1. Here you will put, you will get the value of x. So how actually you will get the solution? So the program size is bigger compared to the earlier two program that we have seen. So how it works, how you can implement this program. So as we have seen, x and y are results for the input a and b. So mainly we have main purpose is to we have to find out x and y. And when you will put this value here, a into x plus b into y, is you will get the answer GCD. But how you will get this x and y value? So x1 and y1 are results for the input b mod of a and a, b mod of a into x1 plus a into y1 is equal to GCD. This we have to find out. So how actually we can find out b mod of a? So to get this b mod of a, we have to use this equation like b minus b mod of a into a. So in Diophantine equation, actually we are doing this same thing. You might have remember, right? B mod of a is equal to what we are actually doing, b minus b mod of a into a. So what we are doing, we are simply replacing it. Like in Diophantine equation, in above we get the following. How? Like b minus b divided by a into x1 plus a into y1 is equal to GCD. So this above is this equation can be written like b into x1 plus a into y1 minus b divided by a into x1 is equal to GCD, right? So after comparing coefficient of a and b, in we get this equation like x is equal to y1 minus b divided by a into x1, and y is equal to x1. So how actually you got this expression here? So like in the program you have to use this one only, but how you get this, how you got this? By using Diophantine equation. But Diophantine equation, manually we can solve the value of x and y by using Diophantine equation. But if you want to implement in the program, you have to calculate this equation. But how we get this equation? We got this equation by using these many steps. By many adjustment, we got this equation. And this equation we will use for to calculate the value of x and y. Okay, so equation that you have to remember, x is equal to y1 minus b divided by a into x1, and y is equal to x1. Okay, so in extended Euclidean algorithm is implemented here. A, b, integer x and integer y values are here. In the base case, initially we are considering a is what? A is 0. So in that case, x is 0 and y is 1, and it will return value of b, and the recursive call is required. So GCD equal to GCD extended b mod of a, comma a and x1 and y1. So in recursive call, we will update the value of x and y. This is the main equation is there that we have calculated here. That is x is equal to y1 minus b divided by a. So x is equal to y1 minus b divided by a into x1, and y is equal to x1, it will return a GCD. Okay, so here from this look point, your main program is started here, in which we are putting a value of a and b, and this a, b, x, y we are passing here in the equation, and finally we will print the result. Mainly three things that we have to print here, like what is the value of x, what is the value of y, and the GCD. We are printing a result here, and these values we are passing to here in this equation, right? And base and recursively we call it, and here from we are getting a GCD. So if you understand Diophantine equation, you can easily solve this extended Euclidean algorithm. So what you have to do,